So we'll be working on that. Right now, though, I think this is kind of interesting stuff. I just Googled and stole all these pictures from the internet. And these are electrochemical sensors. And someone has to figure out and do the math to figure out what this little voltage means for you pick the compound in that half reaction. Okay? And that's pretty much what we're working on today, is we're going to be using the Ernst equation, have a voltage measured, convert that to whatever compound we want. So we can use it to monitor anything, anywhere, as long as we've got an appropriate sensor. Okay? So we don't have the nice pretty pictures, but here's one example. The below cell description describes a probe that can determine the concentration of chloride anions. Okay? Could be anywhere. Write the reactions for each half cell, a balanced net cell reaction, and the Ernst equation for the net cell reaction. Okay? We're on day 34. Is this different than your notes? It's okay? All right, so try it. Write the reactions for each half cell. Okay? A balanced net cell reaction. And the Ernst equation. Yep.
I have a question on this.
Mm-hmm.
There's that carbon on the chlorine side. Is that a typo? Or is that
it's kind of like
that platinum.
this is what Zach is asking, that platinum. When you're trying to find you can write these half reactions yourself or just look them up in the table, right? I mean, they're all in there. Are you going to see platinum in that half reaction? No. What does it do in there?
It's a catalyst.
No.
Something for the H.
Well, I guess catalyst might be right. It's involved in the reaction. It's the metal electrode surface.
That's acting as a circuit.
The surface for the reaction to occur on. The quiz had carbon, right? Because even though the carbon's not involved in the overall half reaction, it's used in building the cell. 'Cause that's what this is. This is building the cell. This is your anode, and this is your cathode. Your anode half reaction, your cathode half reaction. Your oxidation half reaction, your reduction half reaction. It has to be constructed this way. So that's what the platinum is doing in there, even though it's not in the reaction. Okay? I thought I had a table. So go ahead and see if you can figure them out. I'll see if I can blow up a standard reduction potential table. Here's one. It's kind of off. So this platinum, where's hydrogen ion? There it is. All right. There's your hydrogen ion and your water. Okay. Is that, yeah, that's good. The other one has hydrogen peroxide. Okay. And we also need one with, yeah, then we need the chloride going to, and I bet it's not in my table. We're probably going to have to use the book. There were some homework questions that were like that too. Naya, or someone showed me one, had lead fluoride in it. I don't have that in my table. I have to dig them out of here. No one brought their book. Chloride and silver chloride. Chlorine. Shoot. There it is. So don't have your book. You're just going to have to, I can write the half reaction here. So when I write this, when I find it in the table here, do I want to write the chloride, see it as a reactant or a product, the Cl minus, the chloride anion? It should be a, right? We have a phase change going on here. The chloride is the, it's a reactant, isn't it? Right? This guy is going to this guy. And what is this doing there? The electrode surface, right? So you want to make sure you write Cl minuses here. Now it might be flipped in here, so I'm not going to write it exactly as it is in here. I'm going to write it so that I have chloride on the reactant side. So I do have to flip it. Cl minus and Ag solid goes to AgCl solid plus an electron. And I have to flip the E0, 0.197. Okay. And I got to find my hydrogen half reaction. That should be 0 volts. Hydrogen gas plus hydrogen. Did I screw up in the thing? Hydrogen gas plus hydrogen ion. He's still on that side. I wonder if I wrote the dang cell diagram wrong. Because when I look up the other reaction, where do the electrons have to be for the other half reaction? They have to be over here. So I think I wrote that the wrong way around. Right? Because when you look it up, right? So I think these two guys should have been flipped around. I got to change that. Yep. Yeah, I did. When I looked this up in the book is actually, it's a reduction. So the electron's over here. This whole reaction is flipped in the book. And it's a negative 0.197 volts. So I had to flip it. Does that have silver chloride in it?
Yeah, there's two numbers for it. One is with the saturated KCl.
Oh, yeah. Yeah, I saw that too. So I picked the one that was saturated. I got to add that in here. All right. So there's two things that are missing in this, because there's, good, Monica noticed it. There's two of them. There's two E0 two potentials for this half reaction. One is for saturated. The other one says, doesn't say anything, or does it say? Yeah, unsaturated, I guess. So doesn't really matter. Just say it's saturated. Then over here, this should be on that side because, right, reactants, products. Everyone see the mistake? Clear? For over here, I just have to look for something, and by looking at this, I totally disregard platinum because platinum's only showing up once. So that's why I disregard it. Over here, right, I guess you could be talking about silver, but notice how silver, it's not doing anything really. The reaction is involving the chloride going to silver chloride. The silver, no.
So
right?
You add the silver in your half reaction if it's not doing anything?
Oh, did I write down? Well, because I copied the half reaction verbatim. So the silver solid's reacting with the chloride going to silver. So I guess it is involved. Yeah, it is. It is involved. Over here it wasn't. Okay. Yeah, it is involved because it's AgCl.
Okay.
Yeah. If it wasn't AgCl, if it was magnesium chloride or something, right? Okay. Okay. Yeah, I better. So top one times 2. Thank you for noticing that. We've gone through all that work. We wouldn't have seen it. Okay. What's my E0 cell? Do I do anything to this 0.197? Multiplying through by 2? No. Good. So I just end up with 0.197 for it. All right. We'll have 2 silver solids plus 2 chlorides plus 2 hydrogen ions goes to 2 silver chlorides. And 2 hydrogen gas. Okay. So 2 mistakes here. There's 1 mistake, and there's another one. I should say saturated. I'll have to fix that. Okay, so given a measured cell potential, is this everything I wanted? Right, reactions, right? Oh, we didn't write the Ernst equation. So go ahead and write the Ernst equation, given what we have so far. Write a Ernst equation for this. Mm-hmm.
Wouldn't it be negative 187?
We
That's the solid and the electron on the left side. So if you flip it, wouldn't it be negative 197?
Oh, shoot, you're right. So maybe I was supposed to flip the first one. I bet you, if this one is right, I was supposed to flip that one around. It's No, it's fine. This is what's written wrong. These 2 are supposed to be switched around. Otherwise, we're not going to have a positive E0, right? It's a mistake. I didn't write it right. So those 2 should be flipped around so that we would pick this one.
Yeah. Okay.
So did you write your Ernst equation? See if it matches mine. Oh, that's minus, right? Products or reactants. Squared over. Look good? Well, you remember you can't write K, because when do you write K? When it's at equilibrium, and when it's at equilibrium, where's your voltmeter reading in this whole thing? It's which variable? Like which? It's E cell. E cell is what your voltmeter is reading. So if you're going to get a number here, it's not at equilibrium. So this is always products over reactants. And it's either Q or K. You should write K when this E cell is, when it's 0, right? Then this will be the equilibrium constant because you're at equilibrium when this is 0. So they just wanted the Ernst equation, so I assumed they weren't at equilibrium. So that's why I wrote this. But you're always safe writing products over reactants raised to their stoichiometric powers. Okay. Make sense so far? I think that's all they wanted. So we wrote the half reactions. We wrote the Ernst equation. We wrote the balanced net cell reaction. Since we got everything. Given a measured cell voltage of 0.485 volts, find the concentration of chloride in the right compartment. So it looks to me, I see an equation with 1, 2, 3, 4 variables. Well, if they want us to solve for one of these and make it a problem, they better give us how many of these variables? They have to give us 3. And well, they want to solve for chloride, so that means they have to give you the voltmeter reading. They have to give you the partial pressure of hydrogen, pressure due to hydrogen. They have to give you the concentration of hydrogen ion. You just got to look for it. Yep.
Your
did we? Oh gosh, what an ugly mess. Thank you, sir. That's gonna make our math easier, right?
Yeah, so it's just, well,
Right.
that's still 2 on the bottom. It changes.
Oh yeah, that's still 2.
That's all.
But it gets rid of this guy.
The
Ah,
second question is why don't we have anything for EGCl?
he's a solid.
Oh, he's a solid, so we throw him out?
Yeah, that's supposed to be an S.
Okay.
Remember, pure solids and what else don't show up? Liquids. Yeah, so if we had H2O, for example,
And
it wouldn't show
why
up.
did you write P rather than just concentration?
Oh, good, you caught it. I wrote P. I was going to write the concentration of hydrogen, but then I looked up to see what units they gave us.
Oh, it's in pressure.
It's in pressure, so I wrote P. So I shouldn't have. I should have wrote concentration and then, right, and then, oh, hang on, it's in pressure, so that should really be a P. I skipped that.
Pressure instead of concentration.
This is where the Ernst equation is not as, they should be, this is what they should be doing. They should be doing, do you remember the different types of K? We had K and we had KC. KC is where everything is in terms of concentration. Then you had K, and K was called the thermodynamic equilibrium constant. Then P was in units of bar, pressure. So Ernst should be using the thermodynamic equilibrium constant all the time, but the book and homework really aren't consistent with it. The book, they should also be using activities all the time. Then you wouldn't really even care, because your activity coefficient, its units have to match whatever you're working about, so they cancel and you don't really care whether you're in bars or molarity. Just have to.
You're allowed to overlap those units? See,
What I say, use the thermodynamic equilibrium constant expression. Pretty much, if you're given the pressure in bars, then they're assuming you're going to use the thermodynamic equilibrium constant expression. And that's how I would do it. If they change the units from bars to atmospheres, then they should be converting that to bars, and you're putting that in the thermodynamic equilibrium constant expression. Okay? If they give you a gas in molarity, you're just going to have to work with it and use molarity, even though you know that everything should be in bars for a gas. Okay? So I would just, not to make it complicated at all, use what's given. Use what's given. Because whoever made the cell diagram, that's how they expect you to do the calculations with the variables that they gave you. Okay? So you just use what's given and follow that notation.
I was just asking how the units figure in that log. You know,
Okay, hang on.
bars divided by
Remember, all equilibrium constant expressions are unitless because of activities. So this is not correct. We're supposed to have activities in everywhere in here. But it's almost like sig figs. We spend a day on it, and then, okay, don't worry about sig figs anymore. So if your life depended on this, or some $1 million instrument, you would, dang right, you better have activities for every one of these. Activity of chloride squared, activity of hydrogen ion squared, activity of hydrogen gas. You have to have those. pH2, oh, I got to erase that. Zach pointed that out for me. All right? Okay. So now we're just put everything in and solve for chloride. But I think your questions are awesome. This is the hardest part, is just setting this up. After that, it'll be algebra. So substitute in what the voltmeter reads. They had to have given us everything else, and I'm pretty sure they did. Yeah, 1 bar for hydrogen. Here's the pH, so you can get the hydrogen ion concentration, and substitute it in. So just by measuring the cell voltage, they can know where the concentration of chloride is by controlling the pH. How do you get the hydrogen ion concentration?
Just starting with the pH.
Oh, I gotta square it. I will leave it like that. Oh my gosh. Trying not to skip anything here. About 18.4. That's what I got. All right. So you see what I did? I raised 10 to the negative 3.6 because pH is a negative log of H. So that means hydrogen ion concentration is 10 to the negative pH, right? So 10 to the negative 3.6 is 2.51 times 10 to the negative 4. You got to square it, so you end up with 6.31 times 10 to the negative 8. And then just do your little switcheroo thing here. The chloride is on the bottom. So I'll bring them to the top and bring that 10 to the 9th number down to the bottom. Okay, and that's what I did here, right? Bring the chloride up to the top, chloride squared up there, and that big number down to the bottom. So chloride squared would just be those two. Oh, 1 over that. Did I do 1 over? I wonder if I did.
I got like 0.05.
I bet I didn't. 5.3703 10 to the 9th. I bet I didn't. Times 6.31 times 10 to the 8 negative. Yeah, I didn't do 1 over. And then you take, so that's squared is going to be 2.96. So the concentration of chloride, 0.054. Right? This is? So it looks ugly, but to me it's just be comfortable with manipulating these. And your life is easier if you just get all this stuff over to one side, right? Because then you raise it both sides of the 10 power. You just raise that one number to the 10 power. The log disappears, and you're left with what's inside the logarithm. Okay? Where? I don't see where she's looking.
Up when you're like, after you subtract the 0.197 over, and then you divide by that 0.1592 divided by 2, and like the first step. Why is it not like negative on the left side?
This?
Yeah, why is that not negative? Because didn't you divide by negative 0.0592?
Oh my gosh. Did I lose a negative sign, Sochi? I did. So you did the same thing.
Yeah, I did. But
We lost our
I saw
negative
it.
sign.
I thought you were supposed to.
Ah, what an ugly mess. All right. 2.92 times 10 to the 8th is the final answer? Gosh. Yeah, the math is messed up here.
I guess like a second one.
Yeah, ugly, ugly, ugly. But you see the picture on how to, you see the big picture? Because the rest is algebra, and we can work on that. Right? The big picture is you're going to be solving for one of these inside the logarithm. So just work slower than I did so you don't lose your signs. Okay? Let's see if we can, what I can do is I'll fix this up and I'll email you the correct one. Right? Even though you really have it, but we'll fix it. Let's get started on our handout. Right? See if we can get you started on some of these. An electrochemical cell is made by placing an iron electrode in 1 liter of 0.15 molar iron sulfate, and a copper electrode in 1 liter of 0.036 molar copper sulfate. What is the initial voltage of this cell when it's properly constructed? Right? It's also in your book. Right? It's not in there? Huh. I thought I did make it in your book. Does everybody have a handout? I didn't make it in there. That's why it was only 20 bucks. Okay. How do you handle something like number 1? How do you handle something like number 1? How do you handle it? Any thoughts? How do you handle it? Are you at standard conditions? Eustacio, are you at standard conditions? No. So whose equation are you going to have to use? Ernst equation. So we have to write an Ernst equation. So what cell reaction are we going to write? Let's back up. What are the compounds involved in these reactions? Iron with a little what subscript? Iron electrode. It has to be what? An iron electrode has to be solid. Right? Iron sulfate. What's the ion that's going to be involved in the half reaction from this compound? Fe is not an ion. I would be worried about the sulfate or the sulfur or the oxygen if that was involved over here. But I have iron solid, so I have to be just interested in the iron. This doesn't cut it. Has to be iron what? Plus 3?
Is that the 4 minus 2 or minus 2?
It has to be plus 2. Because, see how, if you don't know this, you're screwed, right? So there's one half reaction right there. You just look it up. What's the other half reaction going to involve? Good. Copper plus 2 and what, Monica? Yeah, copper electrode. Copper solid. So you find those two half reactions. How do you know which one to flip? Well, yeah, you want the most positive end result. But the one that you flip is the E0, that's the most negative. That's what I'm, yeah, right? So you're going to look up these two half reactions, flip the one that's the most negative. So how are you going to get the initial voltage then? Once you figure out what the overall reaction is, can't you write your Q in the Ernst equation? Right? Products over reactants. You know what their concentrations are. Right? So you're pretty much set. You know what E0 is. So that initial voltage, can I move on or does someone not see it? Okay, the reason why I didn't worry about, I'm sticking to my guns here and saying the iron plus 2 and the iron solid is because I have no other information about sulfur. Sulfur must not be doing anything. It must be a spectator ion. Because all they said is you have an iron electrode and you have the iron sulfate solution. They would have to tell me something about, if we found a, let's do this. If they would have to tell you something about, now sulfate does have half reactions, right? Where is the sulfate half reaction? Oh, here it is. Okay. If they were going to, if you wanted to involve this sulfate half reaction, they would have to tell you a lot of information, Jamie. They'd have to tell you the pH. Fine, they could tell you the pH. They would have to tell you the pressure for SO2 gas. And you don't have to worry about that guy. But see, they have to give you that information. So if they are talking about, oh, the pH is this and the partial pressure of SO2 gas is this, then I'd be, oh, it must be this is what they're talking about. Okay. And if, in fact, if they still had an iron electrode, fine. You just have to pick the most, because yeah, you can have multiple reactions going on. Just remember, some happen before others. That's how they protect iron from rusting. They put a more reactive metal on there. So, but the iron, yeah, the iron's down here. So for reduction, this one is going to happen before this is going to be reduced. But they have to give you a lot more information if you want to use that one. And they didn't. So that's why I'm sticking with the iron half reactions. Okay. So how about B? How would you handle B?
So the initial voltage is...
Oh, what is, okay, what variable is the initial voltage? It's E cell. Right? Because remember, the voltage is what the voltmeter reads. So in your Ernst equation, you're solving for E cell. You know what E0 cell is? Minus 0.0592 over N log of Q. So you know what all that other stuff is. Okay? Oh, because you have to use the tables. Here's your two half reactions. Here's one half reaction, and there's the other one. And you have to flip the one that Javier said is the most negative. Okay? So we'll have those. And they gave us the concentrations. So this guy's good. How about part B?
Are we supposed to multiply by the liter?
Oh, do they even care? Does the Ernst equation Q has what units? Well, yeah, no units overall. But inside, you put concentrations. So there's no moles at all anywhere. Right? It's all concentrations. calculate the final concentration of copper if it is allowed to produce an average current of 1.25 amps for 335 seconds. Well, I think what if they were, good question, if they were going to use the other one, right? This is products over reactants. You've got an iron +2 in here, and I'm not sure which is on which, right? But let's say this one's on top, and this one's on the bottom, right? If we were going to solve for copper +2, they would have to tell us what the concentration of iron +2 is at that time, but they didn't. So what we need to do is we need to convert this into moles of electrons.
So we did what you showed us on the homework, right?
We're going to, essentially the quiz. Yeah. We're going to convert this into moles of electrons, then we'll convert it into moles of copper +2. Right? And then the copper +2 final concentration would be the initial moles minus the moles that reacted all over the volume. So how do you get the initial moles? Yeah, the concentration at the beginning. Volume, that'll be 0.036. That will be from right here. 1 liter times 0.036 moles per liter. How do you get the moles reacted? That's from over here, right? That guy. So work at it and give it a shot. These aren't easy questions, so you don't let this stuff slide. Come in and ask some questions.